Always ready to start. Okay, welcome to the last session of our school. And now we will have another lecture about super resolution imaging. And it is my great pleasure to present to you Professor Alexander Lvovsky from the University of Oxford, United Kingdom. A couple of words about Professor Lvovsky. He has graduated from the Moscow Institute for Physics and Technology in 1993. In 1998, he has defended his PhD in the University of Columbia in New York City. Professor Lvovsky had a postdoc position at Berkeley University of California. Yeah. Okay. He was leader of a miniature group. This is a special program in Germany for young researchers, and in the University of Constance. Between 2004 and 2018, Alex Lvovsky was professor at the University of Calgary in Canada. And since 2018, he is a full professor at the University of Oxford. And Alex Lvovsky is a totally right person when we want to talk about optical quantum technologies, about experimental optical quantum technologies, their experimental realization. And his contribution is really exciting because it's a lot of its generation of different non-classical states of optics. It's their characterization, quantum memory. So, for example, quantum memory for squeezed states of light. This is his very famous work. And what is especially interesting for us is that Alex Lvovsky is leader of the group where one of the first experiments on super resolution imaging have been done. So if we want to ask once more again, the question which was in Ukrainian segment of Facebook, either we can see, either we can hope to see a coin from the space, yeah? Right person, one more right person is here. Okay, Alex, you're welcome to our school, and the audience offline and online is yours. Alex, we cannot hear you. Alex, something with your microphone. We have to unmute. Can somebody?
You're muted.
You're muted, Alex. Something wrong. Zoom. In Zoom, yeah, something in Zoom. Maybe you should unmute it in Zoom. Still not. You see it's crossed microphone at your side.
Yeah, sorry about that.
Yeah, it works now.
Okay.
Yeah. So you're welcome, Alex.
Okay. Yeah. So, yeah, thank you for the invitation and introduction. Nice to meet you guys. The talk is about, well, super resolution. I think you've heard quite a bit about super resolution already from Gerardo Adesso in particular, but also
Giacomo Sarelli also.
Other. From whom? Who else?
Giacomo Sarelli.
Okay, excellent. Okay. So, well, some of the stuff will be redundant. Then, you're familiar with the Rayleigh criterion. You know that if you have a point source and you try to image it with some kind of lens, then diffraction on that lens will result in
Alex,
the image.
Sorry.
Yes.
No technical problem. Could you please make a full screen because?
Oh yeah, I don't know what I'm doing. Sorry. Okay.
In the auditorium, we
Apologies.
cannot really see text.
Yeah. How about now?
Oh, thank you very much. Perfect.
Yeah. Okay. So an image of a point source will be some kind of blur because of the diffraction on the objective lens. And if there are two sources that are too close to each other, then their images, the point spread functions will coalesce, and you won't be able to resolve them or measure the distance between them. You know that, and you know that in the past, what's going on? That in the past couple of decades, a number of methods have emerged to address this diffraction limit. These methods can be subdivided into three large families. One family involves some kind of near field probing, when we have a source scanning directly over the surface of our sample, and some kind of probe scanning over the surface of the sample. And because there is no lens, then there is no diffraction, therefore no diffraction limit. The second family of methods involve invoking some kind of nonlinear optical effects in the sample. If it's a fluorescent sample, then you can get those individual fluorescent sources to light up one by one, and then you get a sparse image, and it's much easier to localize sparse emitters in comparison with dense emitters. And then finally, there are some ideas involving non-classical light, for example, squeezed and entangled light, that increase your resolution. So all of these techniques are extremely successful. There have been 2 Nobel Prizes for them, but they all have a common feature of requiring some kind of active interaction with the sample. So you need to somehow touch the sample, do something actively with the sample to get a super resolved image. And that reduces the applicability quite a bit. So even within microscopy, there are delicate objects that cannot accept near field probing, or there are objects without nonlinear properties. And beyond microscopy, it's completely out of bounds for any field outside of microscopy, because in astronomy or remote sensing or satellite imaging, there is no way we can touch the sample, we can do anything actively with it. So it would be very nice to develop some kind of technique that achieves super resolution without this active interaction. And if we could succeed, then it would change the face of many sciences. In addition to microscopy, it would change our methods in biology and, as I said, remote sensing and so on. The problem is, though, that, Abe and Raleigh, who developed the diffraction limit science, are intelligent guys, and their logic is based on solid science. And therefore, trying to overcome this seems like a tall order. However, as you know, Man-Kei Tsang, about 8 years ago, 10 years ago, came up with an idea that, yes, one actually can overcome the diffraction limit by, treating this resolution as a quantum sensing problem, right? Quantum sensing means that you have some kind of quantum state coming to you. It depends on some kind of parameters, and you want to find an optimal measurement that extracts these parameters in a quantum optimal manner. And if you approach this problem, then you can actually extend the bounds of resolution by, changing something fundamental about the measurement process. You see, the usual imaging involves measuring the intensity in the image plane as a function of transverse position. And what Man-Kei said is that, this can be changed. So far, all imaging involved this step. And Man-Kei said this can be avoided. So instead, one can decompose the field in the image plane into some kind of basis of transverse modes. Usually Hermite-Gaussian modes, but not necessarily these. And after this decomposition, you measure the intensity in each mode, and then you use measurement results to obtain information about the object. And then it turns out that under certain circumstances, these intensity measurements will have more resolution about the object, more information about the object than direct imaging, possibly leading to higher resolution. The next slides show the intuition behind it. Let's say we measure just the Hermite-Gaussian mode 0,1. So we have some kind of filter that transmit Hermite-Gaussian mode 0,1. I'll remind you what this mode is. Hermite-Gaussian mode 0,0 is just a Gaussian beam. 0,1 is this anti-symmetric profile, right? 2 bulbs, one of them positive, the other one negative. If we are looking at some kind of point source on the optical axis of our imaging device, for example, a single star, if it is on the optical axis, then the image will be completely symmetric. And therefore, this mode filter, the anti-symmetric mode filter, will not transmit anything. The photon detector will not register any light. But if we now displace our star, then the image will no longer be completely symmetric. It will have an anti-symmetric component, and then there'll be some light on the detector. If we have two stars, well, even if the stars are within the diffraction limit still, because they're incoherent, each of them produces some intensity at the detector, these intensities just add. Yeah, and you'll still see some light. You can still know, therefore you'll still know that there are two stars, and you can measure the distance between them. And you can show accurately by means of quantum and classical Fisher information that this measurement can be much more precise than direct imaging. So this plot shows the Fisher information, and I assume you already know what Fisher information is, as a function of emitter separation for two methods. One method is direct imaging, and for direct imaging, Fisher information goes down for small emitter separation, meaning that if the emitters are close to each other, then you cannot really resolve them by direct imaging. And the green line is the Fisher information for Hermite-Gaussian detection, which you can see is constant, does not really depend on the emitter separation, and furthermore, it saturates the limit set by the quantum Fisher information. So as you can see, for small emitter separations, the Hermite-Gaussian detection seems to be infinitely better than direct imaging. Here's another slide that shows the intuition. Well, here's a picture of 2-point sources. Well, here on the top we have 1-point source, or one slit rather, and in this picture, 2-point sources, 2 slits. You can see that if we do direct imaging, in this case, we cannot really tell that there are 2 sources rather than 1, and we can definitely not tell what the distance between them is. On the other hand, for this Hermite-Gaussian detection, we have to distinguish between the situation when there is no light and the situation when there is a little light. And distinguishing between these two situations is much easier than distinguishing between, well, no picture, between some picture and another picture that's slightly different from the first. Right? So this is kind of the intuition behind this formal quantum Fisher information formalism. Since Mankey's first paper, a number of groups became involved in research on the super resolution, including ours. Our group's contribution to this has been to extend the technique to full imaging. So the difference between us and other groups is that other groups have been focusing on evaluating individual parameters of the object in question. For example, the distance between point sources, or the relative intensities, position of the centroid, and so on. And the task that we set is, well, reconstruct the entire image with a higher resolution than direct imaging. And the theory that we use here is quite simple. We, in addition to, well, just Hermite-Gaussian 0, 1, we look at all Hermite-Gaussian modes. And then we can calculate that the photocurrent in Hermite-Gaussian mode Mn, the amplitude of Hermite-Gaussian Mn, is kind of proportional to the mnth moment of the source field. And if we measure in multiple modes, then we'll get multiple modes of that source field. As we know from statistics, if we know the all moments of a certain distribution, then we can actually reconstruct the distribution. So that's the ideology behind the method. We call it Hermite-Gaussian microscopy, or Hermite-Gaussian imaging. Now, this theory applies in the coherent case. In the incoherent case, it's slightly more complicated in the sense that, well, if you do the calculation, you'll see that you can only get even moments. So only get like 2nth moments of the source intensity distribution, meaning that you cannot reconstruct the entire intensity distribution I of xy, but only the even part, meaning that, well, if you do the reconstruction, in addition to I of xy, you will get ghost imaging, ghost images, these additional terms here, I of minus x and y, x and minus 1, y, and so on. And then the question arises how to eliminate these ghost images. One idea would be to just take your object and put it aside, shift it off your optical axis. Then the ghost images will be well separated. This is what we proposed in our original paper. However, in practice, this method has shortcomings because, well, first of all, not objects are infinitely small. Not all objects are of finite size, right? In which case you cannot really separate properly. And second, for reconstructing this object with displaced object, you will need many more Hermann-Gaussian modes, and that creates an additional complication. So what Man-Kei Tsang has proposed instead is to, instead of just a Hermann-Gaussian basis, use an overcomplete basis that also includes superpositions of Hermann-Gaussian modes. As you can see here, in addition to mode 5,5, for example, you add like 6,5 and 5,6 and 6,6. So various superpositions. And with these superpositions, you avoid ghost images. This slide here shows the resolution enhancement that you can obtain as a function of Hermann-Gaussian modes used. Of course, I said in the beginning that if you have all moments of a distribution, then you can reconstruct the distribution. In practice, of course, you cannot measure infinitely many Hermann-Gaussian modes. You have to stop somewhere. And this slide shows what happens when you stop, for example, at 20. If you stop at 20, then your resolution enhancement, in the best case scenario with a Gaussian aperture, will be about a factor of 3. Now, let me tell you about the experiments. There is a number of experiments that we did. First, a couple of technical slides. Mode sorter. As discussed, we need to implement some kind of device that separates the HGMN components, Hermann-Gaussian MN components of the source field. In principle, it is possible. There are so-called multi-plane light converters, which work like this. So you create some kind of phase pattern, usually with a spatial light modulator, and then you make your light bounce multiple times off this phase pattern. And then you end up with each spatial mode traveling like in a slightly different spatial direction. There is even a company that sells these mode sorters. You can buy, it's called Kylab's, company by Nicolas Treps. You can buy this piece of glass for like 70,000 euros. The problem is that they are not really perfect. They are good for separating, for example, Hermann-Gaussian mode 0, 1, but if you need to sort 400 modes, which is the case in our application, then it won't work with high fidelity anymore. So the alternative that we use is heterodyning. Now, it's quite difficult, as I said, to sort Hermann-Gaussian modes, but it is much easier to generate a given Hermann-Gaussian mode Mn. And you can take advantage of this fact by also using the fact that in heterodyne detection, the signal from a heterodyne detector is only sensitive to the part of the signal mode that matches the local oscillator, right? So if you prepare the local oscillator in HG01, your signal will be proportional to the HG01 component of the signal. So that works in practice, as I said, because it's quite easy to generate Hermann-Gaussian modes, but it only works, for this method also has a number of limitations that we'll discuss in a moment. This is a picture of our experimental setup. So what you can see here is laser is split into two channels. This bottom channel is the signal channel, where you generate an object on a digital micromirror device. So far it's not really a proper microscope. It's like a toy microscope where the object is not, it's a sub-millimeter size. It's, not really microscopic. So we impose diffraction limit by placing a narrow aperture in the signal channel, as you can see here. That's our signal. And then the other arm goes into, hits a spatial light modulator, which produces a local oscillator in a certain Hermite-Gaussian mode. Right, so this is a Hermite-Gaussian mode, local oscillator that will meet on this beam splitter, followed by heterodyne detection. This is our object. Of course, it's a university logo. In fact, we don't display this entire logo at a time because for this whole logo, you would require a lot of modes to decompose this image. Instead, we divide it into these subframes and we display one subframe at a time, like is shown here. And here you can see the point spread function. You can see that the size of the point spread function is comparable to the feature size of our object. So that's where we should be able to see advantage due to Hermite-Gaussian imaging. We use 21 Hermite-Gaussian mode in each dimension, meaning 441 modes, and also each subframe here is 21 by 21 pixels. So we reconstruct with 441 parameters. Now, the final technical slide. What one circumstance that we need to take into account is, do you remember I told you that that the signal in that the amplitude of the M-nth mode is the M-nth moment of the source distribution. Now, this is only true in the ideal case, when you have a perfectly Gaussian aperture, perfectly Hermite-Gaussian local oscillator, no dust, no aberration, and so on. In practice, all of these assumptions do not hold, meaning that you cannot really use the math. So what we do instead is we use a neural network instead of the math. And basically, we display a whole bunch of random objects that look like this on our DMD, measure the photocurrents, and then train the neural network to reconstruct the image of this object. Notice that for the label, we don't use the actual object, the actual ground truth object, but we slightly smear it, right? And this is because even Hermite-Gaussian imaging does not have infinite resolution, right? So we don't want to get our neural network to produce features that are not present in the original physical signal. That would result in overfitting. So instead, we slightly smear our label to prevent this. And once the neural network is trained in this manner, then we can show it photocurrents from an object that it has not seen, and it will reconstruct the object correctly. As you can see in this picture, so you can see the original logo, the image of the logo obtained by direct imaging, and the logo reconstructed by our method. You can see significantly improved resolution. You can quantify this resolution improvement by showing our microscope pairs of parallel lines. And you can see that direct imaging can resolve lines that are 110 pixels apart, whereas our new method can resolve pixels that are 56 pixels apart. So you get about a factor of 2 resolution enhancement. Yeah, so this works in this is a coherent experiment. Here we have an incoherent experiment, a kind of similar setup. The only thing is that, well, we have a laser, right? How do you produce incoherent light with a laser? Not easy. Normally, the way people do it is they use a ground glass, so some kind of matte glass that they keep moving, and then light becomes spatially incoherent. We cannot do this, unfortunately, because it would be too slow for us. We need to acquire a lot of data for a lot of modes and a lot of subframes, so that would make the whole thing too slow. So instead, we cheat. Instead, we display these pixels one at a time, and then we add the signals from these pixels corresponding to the object we are trying to display, right? So to display the 0, we add, signal from this pixel, signal from this pixel, and so on. And well, with this, the result become as shown here. You see that with direct imaging, you cannot really reconstruct anything. Well, you see just some strange blur. With our method, you can see quite reasonable quality reconstruction. You can make out the characters. The next question we ask is, can we combine our new resolution enhancement method with existing resolution enhancement methods, namely with confocal imaging? Now, what's confocal imaging? Confocal imaging is essentially when you illuminate your object with focused light, right? And then what happens is, well, your point spread, the illumination point spread function gets multiplied by the detection point spread function. Yes, so if they're both somewhat narrow, you multiply them by each other, you get an even more narrow point spread function. Yeah, that's the idea of confocal microscopy. And the question we ask is it compatible with Hermite-Gaussian microscopy? And do you get cumulative resolution enhancement? And naively, one would say yes, because confocal illumination affects this point spread function, and our method affects this point spread function, the detection point spread function. So they act on sort of two separate ends of the apparatus. So of course the effect should be cumulative. However, when we start to write equations, it becomes somewhat more complicated. So again, the total point spread function is a product of the 2 point spread functions. If both, assuming that both are Gaussian, then you add inverse squares of the point spread function widths to obtain the final width. Right now, in this table, rows are the ways of imaging, columns are ways of illuminating. So for direct imaging, the total the illuminating point spread function is flat. You illuminate in a wide field manner to illuminate the entire object, and therefore the total point spread function is just equal to the detection point spread function. In confocal illumination, however, the illumination point spread function illumination is done by a focused beam, so the two multiply together, and you get resolution enhancement by about a factor of square root of 2, right? If you multiply two Gaussian of the same size, you get a Gaussian that's narrower by square root of 2. Now, for wide field Hermite-Gaussian imaging, again, the illumination point spread function is narrower, but the detection point spread function is half the size, and so is the total point spread function. And now if we combine the two, well, look what happens. The detection point spread function is still half the size of the original, and the illumination point spread function is square root of 2 size of the original. When we multiply the two together, well, there's not much effect, right? Because this is already quite narrow. If we multiply it by a slightly wider Gaussian, the effect will be, well, there will be some effect. So instead of 1/2, you get 0.45, but so the effect is of about 10%. However, well, so it seems like even though the cumulative effect is present, it seems insignificant. But, well, this is the experimental result. And you can see that formally the resolution follows what we expect, right? So the confocal illumination gives us about a factor of square root of 2. A Hermite-Gaussian imaging gives us about a factor of, well, slightly about 2, right? And when we take 2 together, we get slight improvement by another 10 or 20%. But this is not the end of the story, because, well, if you look at this reconstruction here, you see it's much less noisy than the reconstruction here, which means that you can apply deconvolution. You can apply deconvolution, and the deconvolution will further enhance your resolution by another, say, 30%, right? So you see, like in the first site, we said that we should have cumulative effect. At the second site, we concluded that the cumulative effect is insignificant, but then after the experiment, we realized that actually it can be significant because it's not only the reduction of point spread function width, but also reduction of noise, which translates into resolution enhancement through deconvolution. Okay, and now we want to move to proper microscopes. So we started to build a proper microscope. Here you can see the experimental setup. It's essentially the same experimental setup, but now we replace the we replace a DMD by an actual microscopic object, the test target, so-called test target. And the results look like this. If you just take an edge, so the simplest possible object, an edge of a reflecting surface, well, then the resolution is actually quite significantly increased. For wide field, it's like 666 nanometers. For confocal, it's somewhat better. But then if you add Hermann-Gaussian, it's even much, much better. If you try to do more, if you try to do two-dimensional, it doesn't look as great, but it's still, you still have some resolution enhancement. You can see like the width of number one here is better than the width of number one here. So you do get resolution enhancement. And moreover, we tried it with a biological sample, namely a piece of pork tissue from a supermarket. And you can, again, you can see a resolution enhancement. Right. Okay, so that's where our experimental experiments end. And now I want to address a question that is kind of an elephant in the room. That is, how quantum is this whole thing? You see, because when we talk about quantum optics, we usually think about, well, superposition, squeezing, or entanglement. And here we don't have any of that, right? In fact, we declare that we are dealing, we take the light coming from the object as it is, right? We don't try to do anything with the object to get it to produce any kind of special light. But then if it's not quantum light, how come, this is a subject of quantum optics? And the answer is that nevertheless, it is significantly quantum for the following reason. That if light were not quantum, if light were just a wave, then we could obtain our image with infinitely high precision and then simply apply deconvolution, right? And through deconvolution, we would obtain theoretically infinitely high resolution. The reason why we cannot do that is the shot noise, right? Because of the discrete nature of photons, there is shot noise. Shot noise prevents you from doing infinitely precise deconvolution. Okay, so we established that quantumness is important. Now, how important is quantumness in our experiments? The answer is it's not important because in none of our experiments so far have we used have we applied any photon budget. So basically, we dealt with classical light, and we had as many photons as we wanted. So shot noise could be made arbitrarily small. So our experiment is not quantum. The enhancement that we see is more of technical nature rather than quantum nature. But then the question arises, well, will you then obtain any fundamental enhancement in this imaging scenario? I mean, Monkey has shown that you obtain enhancement for the scenario of measuring the separation of point sources, but do you also obtain quantum enhancement in the imaging scenario? Well, to that end, we've done simulations. The simulations are as follows, right? We said, let's have n sources of arbitrary intensity located within a circle of diameter d. And then we image these n objects with different methods, particular Hermann-Gaussian imaging and direct imaging. And we try to estimate the position of each source and intensity of each source. Yeah, so that's the quantum sensing task that we're setting. And well, before I show you the results, I have to define the figure of merit. The figure of merit is as follows. Suppose we apply our method and reconstruct the image to a certain resolution with an imaging system with a given numerical aperture NA. Then we ask ourselves, at which numerical aperture NA prime would direct imaging have the same resolution. Right? So remember that the resolution is limited by the diffraction on your aperture. So if you increase your aperture, then direct imaging eventually will give you similar resolution. Right? So NA prime would be larger than NA. Right? And then we can define the resolution enhancement, which is the ratio between NA prime and NA. And well, that's what our result looks like. Don't look at all of these curves, look at 3 of them. First of all, this blue dashed curve is direct imaging, and that's by definition, it has resolution enhancement 1. I forgot to mention that this plots resolution enhancement as a function of the diameter of this circular object. So this is our circular object, and we plot resolution enhancement as the diameter of the object. And as I said, for direct imaging, resolution enhancement is 1. Quantum Fisher information gives you the absolute limit. And you see that resolution and quantum limited resolution enhancement is quantum limit on the resolution enhancement is significant for small objects. And this yellow curve is this Hermite-Gaussian detection. And you can see that it almost reaches the quantum limit for small object sizes. So that's good news. And then to further confirm these findings, we try to do actual image reconstruction. So we say we have 3-point sources, and these sources are shown here by white dots here. So the 3 sources are the same, but the size of the object is different in these 4 pictures. So you can see the size as a function of, well, the size in terms of point spread functions. And as you can see, when we reduce the size, direct imaging, which is the green spot here, well, in this case, it's very precise. You cannot even see it. In this case, it works almost precisely. But then as you reduce the size of your circle, eventually direct imaging stops working. Hermite-Gaussian imaging, on the other hand, works nicely no matter what this object size is. You see that it reconstructs the position correctly. Okay, so we've achieved so far, right? So to summarize what we've achieved so far, we developed a method that can enhance super resolution by passive observation of the object at hand, using just linear optics and using only far field observation. So we don't touch the object. We've shown that it works for both coherent and incoherent illumination. We've shown that it's compatible with other resolution enhancement methods, such as confocal microscopy, and we validated the technique through quantum figures of merit. What remains to be done in the future? Well, again, we want to make a microscope. To make a microscope, we need to solve 2 challenges. One is the training set. Well, as I told you, so far, we enjoyed the capability of a DMD, which can display any arbitrary image on its surface, and we can produce any training set we want. With the proper microscope, we won't have this capability, meaning that we need to find another way to train our neural network and overcome imperfections of the optical setup. The second problem is heterodyning. You see, heterodyning, the bandwidth of a heterodyne detector is limited by electronics, which is, a gigahertz, maybe a bit more. On the other hand, the optical bandwidth of the signal that's produced in typical fluorescent microscopy is much broader. It's like tens of nanometers, meaning that we cannot use heterodyning if we want to build a proper microscope. It must be a proper multiplane light converter, proper mode sorter, and we need to develop it and we need to adapt it to our needs. Right? And once we succeed, then we'll be able to develop a passive microscope with a resolution which is about a half of the resolution of the traditional microscope. This is kind of a market diagram, what our what the market landscape looks like. So you can see 2 islands. Well, here we plot the resolution along the x-axis versus the price along the y-axis. And you can see two islands. First of all, there are these resolution limited techniques, and well, they are within the diffraction limit, and they can slightly exceed diffraction limit if you use confocal or image scanning or structured illumination microscopy. If you engineer your illumination, then you can slightly surpass the diffraction limit, as we discussed. On the other hand, you have those resolution enhanced methods that I discussed in the beginning, nonlinear methods and near field methods. They can give you very high resolution, like electron microscopy can go down to the size of atom, but they're only limited to specific samples and are very expensive. So our method here, Hermann-Gaussian microscopy, is, well, is somewhere here, right? So it's as expensive as diffraction limited methods, but it gives us another, well, another maybe factor of 2 or 3 in resolution enhancement. Now, the next few slides, I'll show you what we want to do next, sort of the outlook. Computer vision. Think of a variety of computer vision. I mean, first of all, computer vision is a large fraction of machine intelligence market, right? It's about 25% of that market. Second, there is a number of computer vision problems that arise under low light conditions. So even in astronomy, you know, if it's a binary star, you want to know the distance between counterparts. So if you look for an exoplanet, then you want to know the diameter of the orbit of that exoplanet. Or aside from astronomy, if it's a self-driving car, you want to read the message of a road sign that's somewhere far away and not well illuminated, or you want to make out a pedestrian, a cyclist in a dark road, or in microscopy, again, you have a biological sample, you want to distinguish a bacterium from a virus or determine the type of the virus that you're dealing with, right? So all of these problems are united with, the same property that you want to extract certain parameters of your object. So you don't necessarily want to reconstruct the image, right? But you want to extract a certain parameter, like the message of the road sign. And you see the way this problem, the way all computer vision problems are dealt with nowadays is that, well, you have some kind of digital camera, you digitize your image, and then you process the data with a digital neural network. And that's how you extract your knowledge. And as we can have seen from those examples we considered so far, it's not necessarily the optimal way. It is sometimes not optimal to obtain a direct image, right? Sometimes you want to use a different, some kind of different optical circuit. And so far we considered one particular pre-processing way to pre-process light before measurement, namely Hermann-Gaussian mode sorting. But let's generalize it. Let's say we have some kind of optical neural network, some kind of sequence of diffractive elements that transform light in the way we want. Then we detect the intensity of this light, obtain digital data, and again process it with a neural network, right? Then we have an optical neural network and a digital neural network. We can train them in concert, can train them together, and then obtain optimal parameter extraction from these two neural networks. And the good news is that we actually have these quantum tools, these quantum benchmarks, quantum Fisher information for regression and Hellstrom bound for classification that actually tell us what the maximum precision on the parameter of interest can be for the particular state of light that is coming to us, right? So we can check, right? We've trained our neural networks, then we can do the measurements, and we can check if we've obtained quantum limit and what else can be done to obtain it. Here's an example. Well, first of all, I want to say that what we've discussed so far, this Hermann-Gaussian imaging, is actually an example of this approach, right? Because we have a mode sorter, which is in essence an optical neural network. Well, especially if it's like a proper multi-plane light converter, then certainly an optical neural network. and then we have a digital neural network. But the way we do with the way we address this now is the mode sorter is trained for Hermite-Gaussian mode detection. So we don't really, the modes that the basis of our quantum measurement is prescribed, it's pre-programmed. And the question is, well, can we do better than this? This slide answers this question. So again, let's consider the task we started with, the task of measuring separation between point sources that are located within a diffraction limit from each other. And well, you've seen this picture before. You know that the dashed line corresponds to direct imaging. You know that the quantum Fisher information is a constant. It does not depend on the object separation. But then there are three more curves. Let's start with the blue one. Blue one is Hermite-Gaussian mode sorting, but not for all modes. But let's say our mode sorter can only distinguish 9 modes, right? And you see it works almost ideally for small object separations. But then when object separation becomes larger, then the image will not fit into these. The image can no longer be proper. Then this 9-mode basis is no longer complete for the image, and then you start losing Fisher information. Then the orange curve is as follows. The blue curve is ideal Hermite-Gaussian detection. We assume that we have an ideal Hermite-Gaussian mode sorter. But now for the orange curve, we ask ourselves how to build a mode sorter. So let's say we want to make a multi-plane light converter that solves this task, right? Hermite-Gaussian mode sorting for the first 9 modes. And then we will see that the best we can achieve is something like this. So much poorer performance, right? Fisher information barely exceeds that for direct imaging. We don't really get significant resolution enhancement. However, if we instead train our multi-plane light conversion with the cost function being not the quality of Hermite-Gaussian mode sorting, but the Fisher information of our measurement, then suddenly we receive much better performance, right? So again, we train by training our optical neural network not as a mode sorter, but as something that optimizes the precision of our measurement, you get much better performance. So the whole thing becomes kind of a machine learning problem, right? It's a quantum sensing problem, but at the same time, it's a quantum machine learning problem, right? We optimize the transformation on the optical state so that we can reach the quantum benchmark on the resolution. Here's another example of the task. Here it's a classification problem. We try to classify MNIST digits, again, using a diffractive neural network, using just one photon. So we have just one photon coming from our digit, and we try to classify it. And in this case, the quantum limit on performance is determined by the Hellstrom bound. The table here shows pairwise limits. So for example, to distinguish 0 from 1, you want to distinguish 0 from 1, the best accuracy you can achieve is 95%. If you want to distinguish 0 from 9, well, 0 is much more it's quite similar to 9. So the maximum quantum accuracy you can have is 0.87. If you do direct imaging, the performance is poorer, right? So for 0 and 1, you get 0.76. For 0 and 9, you get 0.69. If you use a 3-layer diffractive neural network, you're somewhere in the middle, right? You can do better than direct imaging, although you do not yet achieve Hellstrom bound. So this is what we're doing now. This is the subject of our next experiment, to build an optical neural network that surpasses direct imaging. That concludes my talk. Thank you for listening.
Thank you very much.
Thank you very much, Alex, for this very interesting talk. I believe we have questions. So, we have a lot of questions in the local auditorium. So, Anton, please wait with online auditorium.
Okay. Thank you for this pretty interesting lecture. So I have just one question. As was specified on the presentation, did the typical neural network was used, but if you know what the concrete algorithm was applied for image recognition, just if you know.
Sorry, maybe Andrei, can you repeat the question?
No. Do you know maybe also algorithms which are applied here for direct image? Yeah.
Yeah.
Yeah, algorithm of machine learning.
Okay,
The
I didn't
question
understand.
is that there are algorithms for, so far as I understood, that there are some algorithms for machine learning, the machine learning algorithms which are already applied, yeah, for direct imaging. Yeah, and
Okay.
maybe this is similar performance like this.
Right. Okay. No, that's absolutely valid question. Thank you. Yeah. So the question is, okay, maybe we can just use machine learning to reconstruct this, right? Maybe we don't need this new physics. And the answer is, we tried deconvolution. Deconvolution doesn't really work, but then we also tried machine learning, like proper feed-forward neural network. That doesn't work either for coherent imaging. For incoherent imaging, somehow it works a bit better. It's in our paper. The reconstruction examples are in the paper if you want to look up. For incoherent imaging, it works better. I believe this is because of the way we constructed the incoherent image by adding signals from individual pixels. But for coherent imaging, it doesn't work at all.
Thank you.
No, thank you. Other question? Yeah, there.
Thank you for such interesting talk. And I'm curious about the construction of Oxford's logo, as understood that is a real experimental setup, and that it's kind of shape of real experimental source. So may you say how small is it? And
it's like sub-millimeter size. It's well, again, the whole logo would be probably like a centimeter, right? But because we do frames, each frame is sub-millimeter.
Thank you.
Great. More questions? Yeah, please.
When you have the graph comparing, basically when you were using numerical apertures as a benchmark, you could see that for higher sizes, there is actually a roll-off in direct imaging becomes better. So the question would be, is there some kind of trade-off where this method is better for resolving small details and direct imaging is, is better for resolving higher details? The reason I'm also wondering that is when you look at your Oxford example, with the crowns, the edges are very well resolved using the smooth method, but in the direct imaging method, you can see that they are better filled in.
Right. Yeah. So the reason why direct imaging works better for larger sizes is because, again, if it's a large object, many PSFs, right? So if it's like 20 PSFs, the object, then you would need 400 modes in each dimension, right? Because the size of a Hermann-Gaussian mode is proportional to the square root of the mode number, right? So Hermann-Gaussian mode 1 is 0 is of the size of 1 sigma. That means that to get size of 20 sigma, you need 400 modes, which we cannot afford, right? We only have 20 modes in each dimension, which is somewhere here. I don't think that we see the effect of this in this reconstruction here, because well, as you can see here, the size is quite comparable to PSF, right? So it definitely 20 modes in each dimension can definitely accommodate this. What we would see if the problem existed is that within each subframe at the periphery, we would get poorer quality than in the center, and we're not seeing this.
Thank you. Other questions? Yeah, please.
Thank you for your talk. Maybe simple question. So why can't we get the classical data from like blur image, then we use PG modes and get enhanced image? So why can't we do this in classical compute without using one-to-one? Is it even possible, or do we have some problems with that?
Right. Okay. So I think I'm not sure if this will answer the question, but
Alex, I may translate a little bit because the same
yes.
question appears before. You also know, so you mentioned that you have already classical picture printed, for example, yeah, or some paper, yeah, and after that you would like to apply the same ideology, the same things, so simply to expand this picture in series, yes, and can be done a lot, but as a numerical data, not like this mode. So you do not need, for example, in this case, I don't know, electromagnetic waves, so you have already picture. You can simply numerically analyze this picture, but with the same method.
Right, but the picture that I obtain is this picture in the center, right, by direct imaging. The reason why there is this new physics help is as follows. When incoherent light passes through an aperture, it induces coherences because of the von Sitter-Zernike theorem. And Hermite-Gaussian detection responds to these coherences. It detects these coherences, whereas direct imaging just measures the intensity and the coherences are thrown away. So that's the reason, right? That we take advantage of these coherences that we obtain in propagation through the aperture.
So we lost some information during this. Yeah, okay, more questions? But okay, maybe I'm sorry because Professor Lvovsky don't have a lot of time.
No, I have time. I have 4 more minutes.
Yeah, okay, then okay. Then
it might be a bit maybe it's unrelated, but can we somehow use so in my mind by decomposing into different modes and also doing direct imaging, we're kind of taking 2 different slices of this of our real light data. Can we somehow use this to reconstruct the light field?
Sorry, what do you mean by slices? They're talking about three dimensions.
Yeah. So what I'm thinking is there are technologies to reconstruct not just the intensities of light, but like the
so with space also, yeah.
Yeah, the whole light field.
Okay. The whole.
Can this method be used for that?
Well, I mean, the whole light field, of course, is quite difficult to reconstruct, right? And you need, again, you need to make the question more meaningful. You need to define parameters of the light you want to reconstruct, and it can be any parameters. It can be related to image. It can be related to the 3D structure of your object. It can be related to any feature of the object. The universal reconstruction of the field. Well, for that, I don't think you can get any advantage compared to just direct heterodyne detection of the field, just because if you want to know everything about the field, then you should do heterodyne detection. But if you want some parameters, then measurement on a certain basis would be more appropriate.
Very sensitive measurements. Okay, more questions? Anton, do we have online questions?
No. We don't have any online questions, but I mean, if you have some questions, you have like 1 minute to ask them. So yeah.
Okay. Okay. So let's set our speaker again.
Thank you.
And just 1 moment. So unfortunately, we cannot now do the option-free microphone with Professor Lvovsky, but if you want to have it in an hour, so 19 in Kiev, yeah, you can just tell me, I will